Hello everyone, welcome back to another Intel Minds video. Today I'm going to be discussing a short lesson on antiderivatives. Let us denote some f prime of x function to be, let's say, 3x squared plus 5x plus 2. Now the question is, how do we find f of x? Right, so this is the essence of antiderivatives. We're taking the opposite derivatives, the anti, and we're going backwards. So what you want to know is that if you think about it, taking the derivative of, let's take the derivative of f prime of x. So it's going to be f double prime of x is equal to 6x plus 5, right? This was just how this is going to be. And now if we work backwards, all right, I'm gonna rewrite our f prime of x function 3x squared plus 5x plus 2. So basically when we're going backwards, we're going to want to divide our 6x by its degree plus 1. Degree plus 1, where this is the degree, right? And this is going to be equal to, and its degree is equal to 1, right? In this case, x is 1 and 1, and it's going to be 1 plus 1. And this is the first step. We're going to get 6x over 2, which is equal to 3x, correct? And the next step is going to be, let's just label it step 1, and this is step 2. Next step is we're going to add, remember this is the exponent, the degree, and we're going to want to change that to 3x to the exponent n plus 1. And that is going to give us 3x squared. Now the same thing, let's just take a look at the second part here. What happened to, let's just verify with our 5x. We're going to see that it was originally 5 times x to the exponent of 0, right, which is equivalent to 5, right, because it's just multiplied by 1. And what happened was we divided this by, well, the exponent plus 1, which is in this case just going to be 1, which is equal to 5x over 1. 5x is 1 and 0 over 1. And then which is equal to, it's just going to be itself, right? This is step 1. Step 2, again, let's take a look at 5x to the exponent of 0. We're going to have to change this. We're going to add 1 to the exponent, 0 plus 1. And that's going to give us 5 to the x. 5x to the exponent 1. In this case, 5x. That's how we verify correctly that we went correctly backwards. All right, so now let's take a look at our original function yet again. 3x squared plus 5x plus 2. If we take a look correctly, f of x is going to be equal to, let's take a look. We're going to divide by our degree plus 1. We're going to get 3x over degree plus 1 is going to be equal to 3. And we're going to add 1 to our degree, which is going to equal to 2 plus 1 is equal to 3. Moving forward, we're going to get 5x. Remember, we're going to divide by our degree plus 1, which in this case is going to be 1, so 1 plus 1 is equal to 2. We're going to add 1 to the degree, which is going to be 1 plus 1 is equal to 2. And last but not least, we're going to get our 2 here. We're going to get our 2 multiplied by our x over, well, degree plus 1 is just going to be 1. Because I'm just going to write x to the 0 here, and this x to the 1. We're going to get our degree plus 1 is going to be equal to 1 here. And now rewriting this, we're going to get x cubed plus 5 over 2x squared plus 2x. And then we also have to add our integral constant of c here, because we don't know, there might have been an extra term here that we did not see before. So when we integrate, we have to add this extra integration constants, right? Just show you how that works. Let us say that there was a 10 here, right? If we take the derivative of that, again, let's just confirm our answer here by taking the derivative. We're going to get 3x squared plus 5x plus 2. And remember, this 10, if we take the derivative of it, it's just going to be plus 0. So we're not actually going to see that term exist. So that's why we have to add this integration constant here, guys. That's why the integration constant exists, to ensure that there was some value here that might not be seen. The c could very well equal to 0. There could have been no constant. But to ensure that we have to make sure, we can't just assume that, we have to add this integration constant c. Let us do a few more examples just for some practice here of 5x exponent 9 plus 4x exponent 7 plus 3x exponent 5. Let's take the general antiderivative of this. Give you guys a moment. All right, so the general antiderivative of this is, of course, going to be 5 over 10 times x to the exponent 10 plus 4 over 8 x to the exponent 8 plus 3 over 6 x to the exponent 6. And if we simplify this, we're going to get half x to the exponent 10 plus, again, a half x to the exponent 8 plus, again, a half to x to the exponent 6. And then, if you guys forget, add our integration constant of c. Add it here as well. And let's just verify our answer by taking the derivative. If we take the derivative of this, let's just let this equals to y. Let's just let this equal to y, all right? Y is equal to this, y is equal to this. dy by dx, again, let's bring the 10 down. You get 5x to the exponent 9. Bring the 8 down, and you get 4x to the exponent 7. And derivative of this, 3x to the exponent 5. So there we go, our answer is indeed correct. So that is the general rule that you want to follow here. Let's do a few more examples. Let's take a look at 2 cosine x minus 3. Give you guys a moment for that one. All right, let us take a look. If this is y prime, here this is declared as y prime, then y is equal to, here in this case, we want to take the derivative or the antiderivative of cosine of x. In this case, we have to think about what, if we take the derivative of, will result in cosine of x. All right. So in this case, we will want to, the answer here will be remember, we want to take the derivative of sine x. Oops, sine x. Remember the derivative of sine x, or just the derivative of sine x of is actually going to be equal to cosine of x. You guys remember that from trigonometry, derivatives of trigonometric functions. The 2 is actually just going to remain in front as well, since if you take the derivative of this, it's just going to be 2 cos x. And here, we're going to get 3 over, it's actually just going to be 3x. So that is how we solve that problem there. All right, and one final example. Let us do 10 over x. So y prime is equal to 10 over x. Oh, my apologies, guys. Over here, we always remember to add the plus c. Forgot about the integration constant there. Always remember the integration constant. It's very, very important. All right, so this question, if you take y is equal to, what derivative will give us 1 over x? Well, it's going to be ln x is going to give us the derivative of 1 over x. It's just going to be it's just going to be 10 ln x and plus c. Verify this. Take derivative, dy by dx is equal to, well, guess it, 10 over x. And this integration constant goes away when we take the derivative. And that is going to be a lesson on antiderivatives and how to do these very simple antiderivative problems. You do have to use your brain for a lot of these. Think about what derivatives will result in these antiderivatives. So it might help to think of and just guess and check in the beginning to see, since there is no real rules to these, you just kind of have to remember the derivatives and remember what derivatives will result in what.